Welcome back to The Explainer, everyone. Today, we're diving into a journey that, frankly, scientists used to think was just flat out impossible. On December 24th, 2024, while a lot of us were distracted with wrapping presents or watching holiday movies, NASA achieved something absolutely monumental. They took a spacecraft roughly the size of a small car, and they flew it not just near the sun, not just close to it, but directly inside the atmosphere of a star. Humanity literally touched the sun. And you know what? The data we pulled from that is already rewriting the textbooks.
Okay, let's dive right into this. To even wrap your head around the sheer scale of this achievement, you've got to look at the velocity. During its closest approach, this spacecraft hit a mind-bending, record-breaking speed of 430,000 miles per hour. That officially made it the fastest human-made object in the entire history of civilization.
To put that into perspective, because 430,000 miles per hour is kind of hard to visualize, imagine going from New York to Los Angeles in about 20 seconds. That is how fast the Parker Solar Probe was moving. And at that incredible velocity, the spacecraft eventually disappeared behind the sun and all communication just went completely dead. For a while, Mission Control was flying completely blind.
All right, moving on to Section 1, the coronal heating problem. Why the sun breaks the rules of physics.
So why take this insane risk? Well, we have to talk about the real danger of our star. You see, most people assume the sun is dangerous simply because its surface is 10,000 degrees Fahrenheit. But actually, the surface isn't the main problem. The true danger is this massive invisible envelope of plasma extending millions of miles out into space. It's called the corona, and it presents this thermodynamics paradox that has literally baffled astrophysicists for over 80 years. Think about it like a campfire. The fundamental laws of thermodynamics say that the further you walk away from a fire, the cooler it gets, right? But the sun does the exact opposite. As you move away from the surface and out into the corona, the temperature inexplicably skyrockets.
How much hotter, you ask? We're talking up to 300 times hotter. The corona reaches these absolutely mind-boggling temperatures between 1 and 3 million degrees Fahrenheit. Resolving this exact coronal heating problem was the main driving force behind this entire mission, mostly because it's from this incredibly hot corona that the destructive solar wind is actually born.
Which brings us to Section 2, the solar wind pioneer, Eugene Parker's underdog story.
Before we get into the crazy physics of surviving that heat, we really need to talk about the human element here. Fun fact, NASA had never, in its entire history, named a spacecraft after a living person before this. Back in 1958, a young astrophysicist named Eugene Parker came up with this theory that the sun emits a constant stream of charged particles. He called it the solar wind. But established physics journals actually rejected his paper. They claimed it contradicted known physics. Well, just 2 years later, early spacecraft measurements proved him completely right. Fast forward to 2018, and Parker, at 91 years old, stood on a Florida launch pad and actually got to watch his namesake rocket blast into the sky. He passed away in 2022 at age 94, so he lived just long enough to see his mission set the stage for our entire modern understanding of the solar wind.
All right, Section 3, surviving a million degrees, the engineering trick.
Okay, so here is the massive cognitive dissonance of this whole mission. How exactly do you build a machine that flies into a 1 million degree star atmosphere, especially when temperatures of just 2,500 degrees Fahrenheit will melt steel, aluminum, and titanium? Seriously, take a second to think about that. How did the scientific instruments, sitting just behind this relatively thin shield, operate at a super comfortable 85 degrees Fahrenheit, basically room temperature, while surrounded by a million-degree inferno? Why didn't the whole shebang just instantly vaporize?
Well, it turns out the answer relies on a really crucial distinction in physics, and this brilliantly illustrates the difference between temperature and heat. They are not the same thing. Temperature describes how fast individual particles are moving, whereas heat describes how much energy those particles actually transfer when they hit something. The corona is practically a vacuum. There are very, very few particles per cubic centimeter. So while those few particles are zipping around with million-degree energy, there just aren't enough of them hitting the spacecraft to transfer a fatal heat load.
That being said, let's be clear. The heat shield is still one of the most elegant pieces of engineering NASA has ever come up with. Their thermal protection system is only 4.5 inches thick. It's made of 2 carbon-carbon composite panels, sandwiching a carbon foam core, which is an incredible 97% air. It is extraordinarily light, amazingly strong, and topped off with a special white paint just to reflect the incoming sunlight.
And here's a surprising detail that almost nobody talks about. The intense thermal forces you'd experience at 430,000 miles per hour would literally tear a rigid spacecraft to pieces, so engineers built the frame with flexible joints. They actually designed the spacecraft to naturally bend and flex in response to those extreme forces, so it wouldn't end up snapping right in half.
Moving right along to Section 4, the Slingshot Journey, Navigating the Solar System.
Now, just getting the probe to the sun presented another massive hurdle. Flying directly into the sun is geometrically impossible from Earth. Why? Because any spacecraft launched from our planet carries way too much orbital velocity, meaning it would naturally just overshoot into a wider orbit instead of falling straight inward. To bleed off that excess speed, NASA came up with a brilliant solution using gravity assists. Over the course of 6 years, the Parker Solar Probe executed 7 flybys of Venus. They basically used the planet like a gravitational slingshot in reverse, slowly pulling the spacecraft's orbit tighter and tighter around the sun, almost like reeling in a massive fishing line.
And that leads us to Section 5, the Christmas Eve climax. Into the blackout zone.
Picture this. It's the morning of December 24th, 2024. The team at the Johns Hopkins Applied Physics Lab wasn't exactly celebrating Christmas Eve. They were glued to their consoles, watching their spacecraft fall deep into a total communications blackout zone. To really put this into perspective for you, Mercury, the closest planet to the Sun, never gets closer than 28 million miles. The Parker Solar Probe, meanwhile, was flying entirely on autopilot, completely overwhelmed by intense electromagnetic radiation at an unprecedented 3.8 million miles from the solar surface. It was 7 times closer to the Sun than Mercury ever gets. For 2 agonizing days, they had no telemetry, no beacon, just absolute silence. But finally, on the evening of December 26th, the Mission Operations Center picked up a simple radio beacon tone. Its message, essentially translated to, "I am here, I am operational, everything is working normally." As you can imagine, the room completely erupted in raw emotion.
Section 6. Unlocking Solar Secrets. What the data revealed in January 2025.
By early January 2025, this massive treasure trove of science data finally began downloading to Earth. For the very first time, researchers actually had a view of the corona from the inside, not through a telescope millions of miles away, but right from the inside of the star's atmosphere. And the sheer scale of the discoveries they pulled from this was staggering. The probe's wide-field imager actually filmed the exact birth of the solar wind in real time. It captured a theoretical feedback mechanism they dubbed the solar wind U-turn, where plasma from a coronal mass ejection actually loops right back into the sun. And, most importantly, now what's really interesting about this slide is, it mapped magnetic switchbacks. These are zigzagging magnetic reversals that act as the primary mechanism for transferring energy from the surface straight up to the corona. This data right here is the absolute key to finally answering that 80-year-old coronal heating mystery.
And finally, Section 7, Protecting Modern Civilization. Why this mission matters to Earth.
Let's shift our focus for a second. Why does all of this actually matter to you and me? This isn't just abstract astrophysics. Understanding the sun is urgently tied to real-world stakes for our modern infrastructure right here on Earth. You see, the solar wind creates geomagnetic storms, and right now, the sun is near the peak of its 11-year activity cycle, making these storms way more frequent and a lot more intense. If a powerful storm, say something comparable to the massive 1859 Carrington event, hit us directly today, it could easily cripple GPS systems, knock out satellites, and trigger cascading power grid failures across entire continents that could take months or even years to fix.
Right now, frankly, our vulnerability is extreme. When a major solar storm approaches, we get a warning time of anywhere from 15 minutes to maybe a few hours. That is barely enough time to put our satellites into safe mode. But by understanding the inner workings of the corona through this unprecedented new data, we could eventually build early warning systems that give us days to prepare. We're talking about protecting literally trillions of dollars of infrastructure.
So the absolute crucial point to take away from all of this is simple. For thousands of years, humanity looked up at the sun as this completely untouchable mystery. But we went right ahead and reached out and touched it anyway. I want to leave you with this thought to chew on. As we map the untouchable heart of our star, how quickly can we translate all this new data into a working shield for our fragile modern civilization? Thank you so much for joining me for this explainer. Keep learning, keep questioning, and I'll see you in the next one.